Have you ever just stopped and wondered if our entire universe is, a simulation? It's a wild idea, right? But you hit a wall pretty fast. I mean, our reality feels so smooth and continuous, but computers, they're all about ones and zeros. They're choppy. So how in the world could one ever hope to recreate the other? Let's get into that.
So, yeah, this is the big question, the fundamental problem we need to solve. It's kind of like trying to paint the Mona Lisa using only Lego bricks. No matter how tiny you make the bricks, you're always going to have jagged edges and little gaps. It's just never going to be perfectly smooth. So how do scientists even begin to bridge that gap between the digital world and the real one?
And this leads us right into the heart of the issue, what you could call the digital dilemma. It's a real tale of two worlds, and they couldn't be more different.
Okay, so on one hand, you've got the reality we all experience. It's smooth, it flows, there are no pixels you can see. But on the other hand, you have a computer model, and by its very nature, it's discrete. It's built out of individual little points. Think of it like a super high-res digital photo versus an actual oil painting. One is just a grid of dots, the other is made of continuous, flowing brushstrokes. Now, here's where a simple model totally falls apart. If you just imagine space-time as a bunch of separate points on a grid, things can get weird and fast. A point could just jump to a spot that makes no physical sense next to its neighbors. That would completely shatter the laws of physics inside your simulation. So yeah, just a simple dot-to-dot approach, it's a non-starter. So if we can't just use a grid of points, what's the alternative? Well, this leads to a really beautiful and kind of mind-bending solution that researchers are working on. They call it the elastic in-between. It's like a digital bridge connecting those two worlds. This quote from the research really nails it. Instead of just modeling the points, they're simulating the space between the points. It's brilliant. They're basically creating this dynamic, four-dimensional elastic fabric that connects everything. So it's not the dots that matter so much as the relationships, the constant stretch and pull between all of them. And check this out. This simulated fabric has some incredible properties. Even though it's built on a grid of discrete points, it acts like it's continuous. You pump some energy into it, and that energy spreads out and creates interference patterns, just like it would in the real world. The key thing is, it behaves naturally all by itself. But there's a catch, a big one. So far, we can't control it. We can't tell it what specific shapes to make. But, and this is the really exciting part, even without any control, they've seen these incredible glimpses of what they're after. Just by pure random chance, stable, vortex-like shapes have popped into existence in the simulation, and they've held together for a bit. It's the proof of concept they needed. It's a hint that the ultimate goal here is actually possible. All right, so this brings us to the main event, the absolute holy grail of this whole project. It's a scientific quest, a hunt for one very specific and incredibly important shape. What they're looking for is something called a fermion carrier ball. The idea is that this is a perfectly stable, self-contained, ball-shaped twist in that space-time fabric. If they can figure out how to create one of these, it could literally be the fundamental building block for simulating matter itself. It would be the digital version of a basic particle. And you know something's a big deal in the science world when it has this many different names. Fermion carrier, topology, carrier, ball vortex, whatever you want to call it, they're all talking about the same thing. That one elusive, stable little structure that could change everything. So why all of fuss over this one little shape? Well, because if they can create a stable carrier ball, it would finally provide a foundation, a little anchor, for symmetries to exist inside the simulation. In other words, it would let the fundamental rules of our own universe, the actual laws of physics, emerge naturally from this digital fabric. It's the key to making the simulation truly real. But of course, there's a problem. Trying to find this one tiny, stable vortex in a chaotic, four-dimensional ocean of data, it's like trying to find one specific grain of sand on every single beach on Earth, all at once. It's just not a job for a human. And that's where a new kind of hero enters the picture. To put it bluntly, the scale of this problem is just way beyond human capability. The amount of data this simulation spits out is absolutely staggering. You could have a researcher sift through it for their entire life and never ever find what they're looking for. This is a job that artificial intelligence seems like it was custom built for. You see, where we just see an overwhelming mess of numbers, an AI can spot the faintest patterns. It's literally designed to chew through gigantic data sets and find that one needle in a billion haystacks.
Our brains are just outmatched here, but for an AI, this is the perfect challenge. So the mission for the AI is pretty clear. First, it's going to go in and interact with a fabric. Poke it, prod it, see how it reacts. Second, it's going to actively search through that massive space, hunting for any of those stable shapes that might pop up naturally. And then, the final step, the ultimate goal. It's going to learn from everything it sees to not just find these carrier balls, but to create them on command. And that leaves us with a pretty deep and kind of unsettling question to chew on. If an AI, inside a computer simulation, can learn to manipulate a digital fabric to create the basic building blocks of matter, what does that imply about our own reality? It really makes you wonder, doesn't it? Is our own universe also governed by some kind of hidden fundamental code? A code that we're only just now beginning to learn how to read?